Thank you. Good morning. So I'm going to talk about subseasonal predictability on onset and demise of rainy season over monsoonal regions. So I'm asking one question here: can we predict the onset and demise of the dates, right, of the rainy season? And we'll be using retrospective forecasts. And this is important for agriculture and many applications for water resources. Right? It's an odd thing to forecast. I'm aware of that, but it has applications. So the method to calculate the onset and demise uses only precipitation data. So it's based on this summation here. So PEI is the precipitation at a given day, and PC would be the climatological mean annual daily precipitation, right? So if you start this calculation in the dry season, here's a time series for the blue is precipitation. If you start in the dry season, you start with negative values and they accumulate. And once the rainy season starts, there's an inflection in that black curve there. So I smoothed that black curve to avoid early onsets like these points. And then I take the first derivative of that orange curve, which is the green one. And whenever that first derivative changes from negative values to positive values, I say that's the onset date of the rainy season. And a similar approach for the end of the rainy season. So you start well within the rainy season, and then those patterns will be inversed. And this method is really good for capturing the time where the rainy season is established. So here is just some plots, median value for the onset date. These are Julian days. So notice how the rainy season starts later in the year in the southern hemisphere and early in the year in the northern hemisphere due to the seasonal evolution of convection. And in the bottom here is the interquartile range of those values. And I'm selecting 7 regions for this study. So North American monsoon, South American monsoon, what I call West Africa monsoon, East Africa monsoon, Indian monsoon, East Asia monsoon, and Northern Australia monsoon. I will also point out how low the variance over India is in comparison to all the other monsoons. So again, just observations. These are the mean annual cycle of precipitation for all those regions. And in red here you have the dates for onset and demise. And in parentheses, again, is the interquartile range. So you see it varies quite a lot from region to region. Have a very small variance over the Indian monsoon region, and quite variance over the Northern Australia monsoon. But you see the method captures pretty reasonably the period where there is a shift in the regime. So I'm using forecast from the subseason to seasonal project, and I'm sure you're all well aware of this project. So we have pretty good skill for weather timescales, very skill for climate timescales, and the project is focusing on this gap between weather and climate forecasts. So there are, we use 3 of the models that they submitted: the American model, the Chinese model, and the Japanese model. They vary in the length of the simulations and the period that they cover, and also the spatial resolution sometimes. So for example, the NSAP model starts every 6 hours and runs for 45 days, while the Chinese model runs for 60 days and starting every day at 0Z with 4 members. The Japanese model has 5 members, I think, and they are 10 days apart. So this is a very short time for me to calculate the onset of the rainy season. So what I did is actually I combined observations and simulations. So I append the last year of data to those simulations. And this is the most unconventional part of this talk. Many of the reviewers didn't like this approach. But I'll just remind you that many other papers use combined observations and simulations for the purpose of making forecasts. So here's an example for a forecast of hurricanes and an example for a forecast of the MJO. And obviously, I only analyzed the case where the onset or demise of the rainy season falls within the simulated period. So this is lead time root mean square error. So we have root mean square error on the y-axis here, forecast lead time on the axis here. The climatology, so if you just use the observed climatology to forecast the onset of the rainy season, that's the error you get. So this is consider that whole large region over all the monsoon regions. And so we're using the climatology as the benchmark for measuring skill. And then you have all the three models here with lead time. So 0 would be the time that the observed onset happened. So 30 would be the 30 days before the observed onset happened. And whenever the lines are thick, it means that the difference between the two forecasts, considering climatology or a model, are statistically different. So basically, you take the simulated values over that entire region and for all the years, and you calculate the error in considering the observed values in the same regions and years. So here are the plots for all 7 regions, and notice how usually you have the models outperforming the climatology about 30 to 25 days for most regions. There's a lot of information here, but I would like you to focus on this fact that they outperform the climatology about 30 to 25 days, except over India and East Africa monsoons. There's very low skill there. And now again, it's a different metric for the same purpose, but now I'm looking at a Heidke Skill Score. And in this case, I take the observed values for the region and all the years, and then I rank them, and I calculate terciles, right? And based on the observed values of terciles, I calculate the Heidke Skill Score for the models. So using the 3x3 contingency table. So here I'm also showing 2 dashed lines here, 0.3 and 0.5. 0.3 is usually a common value for predictability skill, right? And 0.5 means that 2/3 of the simulations, the forecasts, fall within the observed tercile. So again, same metric for all the 7 regions. And again, you see how they cross the 0.3 value at least 30 days in advance for almost all regions. And some even cross the 0.5 tercile about 20 days before. But these are consistent with the previous results. So you have Indian monsoon, very low skill, and the East African monsoon also very low skill. So here I'm looking at the mean square error divided of the simulations. So I'm sorry, this is wrong. And divided by the variance of the observations, which is pretty much the mean square errors of the observations if you use the climatology as the predictor, right? And these are forecasts for all the simulations within week 4, lead times week 4. So what you want to see here is blue and green and purple, right? These are good values. So you see over most of South America, West Africa, East Asia, and Northern Australia. And they're pretty similar in all 3 models. And I'm showing also the MME of them here. So it's pretty consistent across the models. And the reviewers always point out about the issue with discontinuities in the time series because I'm appending observations to forecasts, and also biases in the model could affect the perceived predictability, right? So here it's just the precipitation bias for week 1 to 4. This in the case of onset dates, and this in the case of demise dates. Sorry, I didn't show the results. I did all the same results for the demise, and they are very similar to the onset, so I'm sparing you of seeing the same graphs over and over again. Here are the bias of the precipitation, and I'm considering only the multi-model ensemble for this plot, just to illustrate. And you see that most of the regions, the models have positive bias. small regions like South America and perhaps East Asia has negative, but mostly positive bias. And here what I'm showing is the spatial average of that S curve that I showed in the beginning, the curve that we use to calculate the onset and demise dates. So in black would be the observed curve, and in red would be from the simulations. So what we found is that there isn't much of a discontinuity in the time series, and the bias, the role of the bias in the models is the inflection of this curve, right, which is accounted for in the metrics we use to evaluate the skill of the models, like root mean square errors and Heidke Skill Score. So there isn't much effect of bias and discontinuity. So conclusions, we use a combined approach with observations and models, and the message is that if you take advantage of the observations, you can have forecast skill on subseasonal time scales. We noticed that the skill for the onset is good over North and South America, East Asia, Northern Australia. Spur of India monsoon region is similar for the demise. It's good over North and South America, East Asia, Northern Australia. It showed a fair skew actually for the monsoon region in the demise plots. I listed most of Africa as uncertain here because if you do the same methodology with a different precipitation, forgot to mention I used CPC data in this study, but if you use TRIM, for example, you have the same results except over Africa. So I'm listing uncertain here. And I think this method would be valuable, addition. So if you use conventional methods that focus on the large scale of the monsoon, this could be an addition to that because it has the advantage that you could actually provide information at the same resolution of your data to decision makers. And AMS asked a survey about the data, so for this particular case, basically what I need is better precipitation data, better coverage in spatial and time, and better quality control precipitation, especially over developing countries where you have usually monsoons, right? So thank you.
Well, pretty very good on time. So open for a few questions.
So I noticed that the onset and demise are not always similar. So sometimes you have very fast onset and very slow demise, or the other way around.
Right.
I'm a bit surprised that they have the same thing.
Right.
There not enough difference between a slow onset
I think there is some difference if you look at the curves more closely. You will see some difference. But the fact that we smooth the curves, I think, it helps with the predictability in some way, but also kind of averages them out in a way. So there's a two-way effect in there. I don't know if I answered your question.
I noticed that they made usually not this one, but the others is more rock in the ways that it goes up and down. The other two models has a more smooth one.
Oh, right.
Do you have a reason for that?
Yes. So it just very simple. So if you consider that the rainy season is varying over time, so the onset date it changes with time, right? Because the Japanese model only starts the members every 10 days, you have a gap in there, so that leads to that behavior. Yeah. Maybe. Yeah. This behavior. Yeah.
Thank you very much. Any other questions? A couple more minutes. Chair, we're asked to keep it on time. If we end early, we should wait until the time begins.
You're welcome. Okay.
Are you planning to use the other SOS models for this that have more temporal?
Yes. Right. Yes.
And what do you expect to change that?
Well, I really wanted to use the ECMWF, right? It's considered the best model, but we didn't get the data before I did this analysis. So we got the data now.
Just curious about that. Why? What's the motivation for you using CLA model?
It was basically the models that we have at hand at the time. Yeah, it's a lot of data to download and process.
Okay, thank you again.
Okay.